Well, it's 6 o'clock. Welcome back, everyone. For today's class, we're not doing anything too crazy with probability. We're going to start off first with the review problem in section 4.2, like we discussed. I have an extra example 4 posted on those notes. Then we'll turn to section 5.1, finish this one off. We're pretty close to done on that section. I think we're really just going to be scratching the surface in section 5.2. So we may not get too far, but we'll still be on really great track with where we should be on the syllabus. Well, any questions at all, folks, before we get going with our work today? Okay, well, let's do another adventure of this least squares regression type analysis. I'll clear these off, and here's our fourth example. So just like before, we have a table of values, some values labeled as X, some values labeled as Y. This is kind of helpful in a way because it's just labeled X and Y right away. This has got to be the explanatory data on the left, and this has got to be the response data on the right. And looking at the scatter plot to the right, dive depth is the horizontal axis, so that's all these values here. The maximum dive is the vertical axis, so it's the second column. And the data says, well, to start off the context, scuba divers have a maximum dive time they cannot exceed when diving to different depths, which is really serious. Diving is probably one of the more dangerous things you can do, especially as recreational sport. It says next, the data in the table below, provided below, show different depths with maximum dive times in minutes. So if you were, say, a professional diver, either for work or a recreational diver, say you know you have a job to do at 80 feet, you should only be diving for 35 minutes by this table here. And 80-35, that would just be this dot right here on the scatter plot below. So dive depth, again, just to confirm, is going to be the explanatory variable. The maximum dive time will be the response variable. And first thing we want to do is calculate the least squares regression line immediately for these data. Well, first thing we have to do then is just throw this into the calculator. And this problem I brought here today, this is more in line with probably what a real exam problem would actually look like. It has 6 observations for each variable, which is not too much to worry about. And it's not too many digits to type in. There's not like 3 decimal places of data, so we have to be highly accurate. So this is meant to just kind of go into the calculator pretty efficiently. So I'll type in the first column, 50, 60, 70, 80, 90, and then 100 feet for the dive depths. Then to the right, just the times in minutes. So if you're diving 50 feet, you have 80 minutes before you start to have trouble. Then the time starts to shorten up rapidly, 55 minutes, 45 minutes at 70 feet, 35 minutes, 25 minutes. And then if you go from 90 feet to 100 feet, those 3 minutes really do matter. So on that 100 feet, only 22 minutes. So that's all of our data set up. Next thing to do to get the actual regression line, hit your stat button, calculate, and it's option number 8. You can just click on 8 if you're getting a handle of it, or just scroll down. So with that all set up, we've got it, folks. That's our least squares regression line. I mean, it's broken up into parts. When we go to actually put it down on paper, we're writing down this first line, but filling in the value for A and fill in the value for B. Well, does that look all right to folks? Anyone getting something wildly different, or are we getting about the same results? Sounds like we're all happy. So let me grab this. I'll only copy to here, just to emphasize that's the information you really need. And so the official answer for this is going to go y equals, I'll color code the intercept. We're doing 2 decimal places of rounding on this one. So it's going to be 127.24. Then next is going to be a minus, since our slope takes on a negative value. And I'll put the slope in as green. So 1.11 multiplying x. And you don't have to box your answers, but I do that in the notes sometimes, especially if there's other stuff like the calculator output on the left. That's all you would have to write to solve this question here. Well, we have our regression line. If we were to try to plot that thing, it might look something like this. The instructions didn't say to do so, but that would be my best attempt on putting that line to the actual data. Looking at the data itself, it's have some pretty interesting observations, but nothing too majorly out of order. So next thing we're going to do is just go down the motions like we did before with the other examples. We want our practical interpretation of the slope, so that's a good place to start. The slope itself is going to be the number in green. Best way to memorize it is it's always the number multiplying x, whereas this constant here is going to be the y-intercept. So if we're going to interpret the slope, we can say right away, b is equal to negative 1.11. I should keep that in green. That negative came from right here, so it is part of the slope. Divide by 1. And next thing we need is units for this thing. I don't know why I put 1 in black. We can keep that in green. So there's definitely a trick to this. Anyone recall how to get the units for the denominator on this fraction? As kind of a mnemonic device, one way to think about it is, if you're looking for the units of the denominator, go to the graph, and the unit would be on the bottom of the graph. So that's a decent way to think of it. Think of bottom here. The unit would be that portion, bottom of the graph, feet. So it says 1 foot. Then for the units in the numerator, anyone spot what those ought to be? Exactly. So it's going to be the dive time in minutes. So we'll put here, you could put dive time in minutes, or if you want to abbreviate it, you could just simply say minutes. Also, I think dive time might be actually better if we're going to give a practical interpretation. So let's go with dive time in minutes. Negative 1.11 dive time in minutes. If we want to be more descriptive on the bottom, it's okay to just call it feet, but you could also say 1 foot of dive depth. You know, I also think that might be a little bit easier getting down the practical interpretation because it's just more descriptive when you put down not just the unit of feet or minutes, but what's actually really happening with those units. Then the practical interpretation from here, really not too bad. Let me type this out. Practical interpretation. I'm pretty sure I spelled that wrong. And it would be something along these lines. We focus on the denominator first, and we say, for each additional 1 foot of dive depth, sorry, I had trouble spelling the word depth. We're in better track now. We can say the amount of time for diving, the dive time for that particular dive will go down by 1.11 minutes. So let's write that next. For each additional foot of dive depth, the dive time must be reduced coming from that negative sign. And it makes sense, the deeper you go, the less you're allowed to stay in the ocean. Must be reduced by 1.11 minutes. So that's what the slope is saying altogether. And visually, if we put a line to this, it's saying you go to the right by 1 unit, kind of hard to see, I'd have to zoom in a bunch. You'd have to go down by 1.11 minutes, is what that slope is saying there. So that's our third interpretation of a slope like this one. And just for the sake of giving you a feel for what would be expected on a quiz or exam, it has to have the context. So we have to be mentioning something about feet and time. So we have to say for each additional foot, that's the denominator, including its unit. Then we have to say what happens in the numerator, reduced because of the negative sign by 1.11 minute. We also have to mention we're talking about dive time, but I just didn't want to highlight the entire thing in yellow. But to me, those are the major things I'd be looking for a correct interpretation. Any questions at all, folks, on running through that one? Okay, riveting stuff. Now let's try the next interpretation. Well, this one's not an interpretation, this one's a computation. It says, suppose you are a professional diver, so congratulations, it pays well, it's just extremely dangerous. And you're about to dive to a depth of 88 feet. That would give me the heebie-jeebies. Looking at the table, well, you know, at 80 feet, it's 35 minutes. At 90 feet, it's 25 minutes. So I think a lot of people would just set their dive timer to 25 minutes. That's on the safer bet. But if you're a professional diver trying to get a job done, you probably need to tune your clock, your dive timer, to the exact amount you should have it set to at 88 feet. We can do that with this equation right here. First thing we have to do is write down y equals 127.24, put in a minus 1.11. And the value in question here, diving to 88 feet, that's what's going to take the value of x. X was the horizontal axis for dive depth, so it does make sense to throw that inside here. So I'll just put it in without the unit, just 88. So the output is going to be time in minutes. And here's what we're going to get on this computation. It's first 127.24 minus 1.11 times 88. And it's telling us that your dive timer should be set to 29.56 feet. Looking at our data here, let's take a look. At 80 feet, it was 35. At 90 feet, it was 25. We threw this into a least square regression line, and we got 29.56 feet. That could actually be dangerous in a certain sense. Does that make sense to folks? The problem with least squares regression is it's just a line that's trying to get close to all these dots, but it can't do it perfectly necessarily. In fact, these dots have kind of a strange shape going about them. I drew a straight line since that's what we're doing in this problem, but you know, a line that kind of goes like this might have been better for these data. So if we put in a straight line and do regression analysis kind of uncarefully and get a time that's about kind of the way it looks right, we use a least squares regression, 29.56 minutes. But if we're not paying careful attention to what's happening with the data, whether or not a straight linear line should have even been used to model these data, that right there could actually be deadly here. Because the table once again says at 90 feet, should have been 25 minutes. We are predicting 29.56 minutes. So least squares regression is a powerful tool, but this is one of those problems where a professional diver probably would not do this. They would probably really tune their clock to 25 minutes, maybe just a little bit longer, 25.5 minutes. Well, as far as the instruction said, we followed it to a letter, and that's what the recommendation would be, 29.56 minutes, which sounds very dangerous. Well, any questions, folks, on getting through this part C? Or excuse me, yes, part C. Okay, one thing that's, again, really tricky about regression analysis is putting down a straight line sometimes looks like it's about the right thing to do, but it's not always going to be the best line of models. If you're curious about this stuff, our book goes a little bit more into model checking to determine, is linear even appropriate, going beyond just looking at the dots. But if we keep on going through this problem, let's see what else is next. We're getting into our interpretation next, and it's asking us, does it make sense to interpret the y-intercept of the least squares regression line? Here's the y-intercept of 127.24. That would be in units of minutes. And how do folks feel about this one? Is a y-intercept sensible? Should we tune our clock to 127.24 minutes? Or is that kind of a nonsense value in this case? Some saying it's a nonsense value, or we might be able to do that. Honestly, it's really kind of tricky, right? The slope you can always interpret, but the y-intercept, it's always going to be about context. So here's what I would do to start this off. Let's just take a screenshot here just to remind ourselves of what x and y are. They're asking us to interpret a y-intercept. And the only way you get to interpret a y-intercept is if you're plugging in x equals 0 into the data. So let's say, probably should go to a new page on this one. At a y-intercept, x would be 0. And what is x? Well, its unit is in feet. So it'd be at 0 feet. Well, would that make sense to folks in this context, having 0 feet? I agree with the no on this one. Imagine you are a professional diver and you're trying to tune your clock to determine how long you should dive for a dive that is 0 feet. Well, that would mean once you go to dive, you're just going to smash your head into the ground, right? There's no water to dive into. And that's the tricky thing about this one. At 0 feet, there is no water to dive into. So although the y-intercept, it's a quantity, it's 127.24 minutes. It's a really long dive apparently. But if we put that value on the graph, we'd be carrying this line further and further to the left. We have a nonsensical dive. You have no feet of water to dive into. And so that means for this problem, the y-intercept has no meaning or interpretation. Well, does that make sense to folks on the problem with the y-intercept on this part D here? Yeah, go ahead. Oh, that's a good question. For the x equals 0 portion, let's take a look at 4.1, I think. No, maybe a better one might be 2.4. So the idea with that one there, let's see, I'm trying to look for a problem I thought we did. Oh, it's because it's on these notes. Sorry, back to the top of these notes. Here's what happens with a y-intercept. A value that's a y-intercept is always found by plugging in 0 for x. So on a graph like this one, this is what it looks like. Your x coordinate is 0, and your y-intercept would be right there. That point itself would be at coordinates 0, -5, where the -5 came from that portion right there.
It's not like on a graph or doing like a chart, how exactly do you know where that 0 is?
Oh, I see what you're saying next. So like on this chart right here, it's a tricky chart because it doesn't actually show the origin. You'd have to imagine something going like this. It's going off to the left. Eventually, we actually hit the true, I don't want to put it there, the true y-axis would be right around here. This line then would carry off, clear over to here, and there's your y-intercept. It was about 127 minutes, roughly, at that location. So the trouble with these kinds of graphs is, when you see a scatter graph, they're not always going to put the origin on the graph. They're only going to show you the portion where your data actually lives. So there's no data here. It wasn't even plotted.
What if it's being positive? Right?
Going upwards, then it would have looked more, say, like maybe something like this instead. It'd be a different scatter plot, but then your y-intercept would have been in that location. Y-intercept is just where you cross the y-axis, and that's always, no matter what, where x equals 0 for your first coordinate. You mean like on this graph, it'd be somewhere above or below? Or do you mean the actual number, like 127?
Yeah, like that.
Well, the number 127 wouldn't be a guess on these ones, because if you plug in the x-intercept of x equals 0, your 0 would go right here. That would mean the negative 1.11 times 0, and you get 127.24 in minutes. Does that make sense with those questions there? Awesome. It's definitely a tricky topic, but I'd say the best thing to always remember about this is if you see a question about y-intercept, your immediate thought is that means x is 0, no matter what. Then you have to judge in the current problem, does x equal 0 even make sense? Sometimes it will, sometimes it won't, like in this example. Other questions or comments at the moment? Okay, well, let's see what else we have going on these. I think, oh, that was it. This one ended really fast. Kind of strange, but that's pretty much what's going on with regression analysis for our class. This kind of topic can keep on going and going and going, but for the sake of an introductory class, I feel like we've achieved that. We've introduced the topic. So your quiz is very similar to example 4. I'd say it's more similar to example 3 here, just not as much context, but all of these examples will be really helpful. And when we go to do these on exams, it's pretty much going to look like these examples too. Essentially, my quizzes are my way of showing you what an exam problem would look like for any given topic. Well, I guess we're done with these notes. Any last questions, folks, before we save and close these? Yeah, go ahead.
So when you're answering the question, it's asking like, what would you predict, whatever it is, where you're like plugging in a number for x.
Mhm.
When you answer that question, do you answer it like just as y hat equals whatever it is?
Oh yeah, absolutely. I in fact just forgot about that one. This one, the better answer would have been y hat. I take it either way, but y hat is emphasizing you're giving a predicted value. So that's usually the better way to write that. Thanks for mentioning that. That was my complete omission on this one. Glad you mentioned it. Now it's saved in the notes. We have the better answer right here. Any other questions at all, folks? Okay, I'm going to have this saved up. And now let's go to where we left off on section 5.1. We're kind of jumping around because we decided at the end of class last time, when we finished 4.2, we wanted another example. Then we got to this stage when we were getting through the notes in section 5.1. We were just introducing the probability topic, but the short of it is, if you see something that is indicated with an absolute, or excuse me, a capital P with parentheses or round stuff, this whole statement here is just read as the probability of the event D or the event A occurring. This little symbol here, it's odd. We're going to see a lot of odd symbols like this. But it's just a union symbol. So it is the union symbol. And you'll see the union symbol whenever an or is written down, like on this one here. Now, this is an extremely strange kind of or. Usually when we say the word or, it might be something along the lines of it's raining outside or I'm staying at home. Well, that means you usually would hear that as either it's raining outside or I'm staying at home, but not both. We usually think it's one or the other, not both at the same time. This or is very different. We calculate the probability that the randomly selected book is a digital book or an audio book or potentially both. Even though that couldn't happen on this one, in other problems, that's what that or is doing. It's a really strange kind of or. So it happens whenever you're dealing with the or symbol, which is called an inclusive or. We'll mention that a lot more when we're going to the next notes, but we introduce the union symbol right here. That's a good time to mention those kind of matters. Well, in this kind of problem, we're just looking at the different kinds of books that the bookstore was putting out. These were the actual probabilities from the historical sales in the past. So say, for example, if we look at that column, it's saying the past sales had 16% hardcover texts. So now our part B is asking, what is the probability that a randomly selected text from past sales is, well, not a hardcover? Just like on part A, the word not is also really important in statistics. And it also has its own symbol that we have to tack on. The way we would write this is we coded H for hardcover. So if I write this, That's the probability of H. And we put a superscript, like if you're squaring something, this is where the power 2 will go. And that thing is read as a complement. It's a way to say not H. Let's write that down as well in the notes. H with a C here is H complement. And it is the event H does not occur. So that word here, not, is a symbol whenever we go down, write down these events. And it means we're looking at the probability that it was not a hardcover. And that means it's also tied together with this complement rule above. The complement rule says the probability that an outcome will not occur, that's this, H does not occur, is equal to 1 minus, let's write that in, equals 1 minus the probability, so we'll put in an uppercase P for probability, that the outcome will occur. Well, the outcome actually occurring, that's H itself. Kind of a strange formula. There's really two ways to do this, but sometimes this is a very, very powerful formula to have. Let's try it this way and see what it would have been if we did it in a different method. This is 1 minus probability of H. We go up to the table. Probability of H is 0.16. So 0.16. Subtracting gives us a 0.84. So that means there's an 84% chance that the book selected was not a hardcover. So that's one way to do it. But I think if I was doing this problem and I wasn't trying to show the complement rule, I would have done it differently. This is what I probably would have done instead. If the question says not a hardcover, I would go to everything that's not a hardcover, that's paperback digital audio, and add those probabilities. So 0.36 plus 0.40 plus 0.08. That gives us the value 0.84, which is exactly what we have here. So you can do it one way or another. And the reason this always works is one extra bit of information. All of these probabilities must, that's always a strong word when we say must, add to 1. And that's 1 exactly. So if we're asking for the probability that something doesn't occur, we just take 1 minus the probability it does, because everything would sum to exactly 1 in this probability table regardless. So that's 2 probability statements down. Example 3 is really our way to start showing some of these interesting formulas and interesting symbols like the union symbol, complement symbol. And that's the only one I have so far. Part C is just a standard kind of computation. Any questions at all, folks, on getting through A or B? Yeah, go ahead.
So when we're finding probability, it's fine to just leave it as like the point, whatever, the decimal number.
Yeah, absolutely. I would say in WebAssign, sometimes that's what they're going to prefer as well. So if it asks for a probability in WebAssign, they're expecting the decimal answer. But if it's for about quizzes or exams, I'm not too worried. If you give me 0.84 or if you give me 84%, I'm happy to take either. It's really just a change of unit. Other questions so far? Okay, well, let's finish off this last one, part C. It says, what is the probability? Let's read the whole sentence. The whole sentence really goes like this. If a purchase from the past sales is selected at random, just one book purchase, what is the probability that this purchase for a book is for a book that is a printed book? So the way I'd probably write out this one is probability of a printed book. Now this looks a little bit weird, but sometimes when we write down a probability statement, we just write down the event in an ordinary way. So that's always fine to do as well. If you wanted to, though, you could say, well, what's a printed book? That'd be the hardcover book. So we can put H there. Or because we said the or, we were going to use the union symbol again. The other option was the paperback book. So it's going to be H union B. But really, at the end of the day, we're just grabbing these two probabilities and adding them together. So from the table, it's 0.16 plus 0.36 equals 0.52, meaning there is a 52% chance of obtaining a printed book. These are the non-printed book. This was a 48% chance. And so these two, once again, they have to sum up to 100 because they were talking about different values in the table above. Well, we did it, folks. That's running through probability on this question here. Any questions or comments on this introductory example? Okay, well, I guess we're ready for section 5.2. We have 19 minutes, so we're not going to try to finish it for sure. Just get started and see what's going on in that next section. One thing I do want to remind folks about is when we did this problem right here, example 2, part B, this was really the major thing we need in sections 5.3 and 5.4. Once we start cranking out more and more probabilities, 5.2 turns out to still be kind of an introductory section. There's just a lot of nuts and bolts when it comes to probability theory that we have to get through first. So let's take a look at 5.2. It's right here on the Moodle website, but since we're not finishing it, it's going to be moved to just the next week, right down below. And here's how it starts. We're trying to give better definitions to things that we were discussing before. When we do probability theory, it means there is some kind of random experiment, or as our author likes to call it, a chance experiment. Anything that's a chance experiment is some kind of experiment where, not like an experimental design, but more just a procedure where you know what all the possibilities will be. Think flipping a coin. I know I'm going to get heads, or I'm going to get tails, or a weird possibility where it lands edgewise, but we don't talk about that as much unless we're being really, really pedantic, I guess. So in a chance experiment, you'll always know what the outcomes are, but you will never be able to predict what the next outcome will be until the actual thing happens. So just like with flipping a coin or tossing a dice, we know everything that'll happen, but not what will happen next. Then, once we design a chance experiment, whether you're tossing a fair die, a fair coin, or something more convoluted, we collect all the possible outcomes, all the results rather, into something called the sample space. A sample space will usually denote by letter S, but occasionally in some problems, S could be an event if it makes sense. It could be S for schools or something like that. So our goal in this problem is we want to describe a sample space for any one of these situations. Well, there's just a part A and a part B. We're going back to our initial example in section 4.1, where we're tossing a fair coin. In determining the sample space S, essentially, really all we have to do is say, toss a fair coin. All of the outcomes, that's a sample space. Because it's a set, we open a curly brace like this and put in all the objects. We can get either heads, H, or tails, T. So that's what the sample space would look like in that random experiment. Well, any questions, folks, with writing down the sample space? Okay, that's essentially what we did in section 5.1. Only thing is new is we put parentheses around it. We called it S, and we said that's all the possible outcomes. Then, next question we want to wonder about are the outcomes equally likely? Well, we kind of discussed that as well before. Folks said there's a 50% chance of heads, a 50% chance of tails, and that's because we're dealing with a fair coin. That alone is enough to tell us the outcomes are equally likely since probability of heads is 0.50, or you could say 50% if you like, and probability of tails is the same, 0.50, under the assumption we really have a fair coin. So that's what happens in that sample space there. Kind of just a review of what we did on that first example. Any questions at all, folks, about writing down the sample space or determining if it's equally likely? Okay, let's change gears to a new experiment. Before we were tossing one coin, so we're going to up the ante. Imagine tossing two fair coins now. We're going to toss two fair coins. Imagine doing this yourself and record the number of times tails is facing up. Are the outcomes equally likely? So if we toss two fair coins, record the number of times tails is facing up. Any volunteers for what that sample space would look like? Yeah, go ahead.
We just have to.
Not quite. You're close though. The trouble with this one is what they're going to be doing in this random experiment is just record the number of times that tails is facing up. So that's what's going to be going inside this sample space. Suddenly they're changing gears on us and it's a weird chance experiment. Two things kind of happen. Two coins are tossed, then we observe the outcomes and we just put down a number. That number will correspond to how many times tails occurred on those 2 coin tosses. Right, that'd be one possibility. Say we toss two coins, we get tails and tails. That's probably how we would write that out. First toss is tails, second toss is tails. That would mean we have an outcome of 2 altogether, right? And that's pretty much the good way to think about it. Imagine really running through the experiment, go and record the number of times tails faces up, and we get a 2. Yeah, go ahead.
And then you have tails in, tails, tails, heads, tails, and heads, tails.
Exactly. So those are everything that could actually happen, right? After we toss the 2 coins. Then the values we record would be 2 on this, tails came up twice. 1 on these 2, tails came up once. And 0 on this one, tails came up not at all. So it says record the number of times tails is facing up. And we've got it now. The sample space goes 0, 1, 2. So excellent work. That's how we would build a sample space in this situation. Really different, definitely different, right? Going from tossing 1 coin and just recording the outcome versus doing 2 coins and recording something else, a further result would give us that sample space. Yeah, go ahead.
Why we don't do that either?
Oh, that's a great question. It turns out with sets like these things, let's see, put this in a comment pen. A set only records the unique elements. So that's one thing that's a little bit weird about probability theory. In probability theory, we're actually doing set theory, and this is just one of the weird things that happens in set theory. Any set cannot contain duplicates as a mathematical set, and this is one of those weird situations. Thanks for mentioning that question. That's definitely a big oddity with this one. Other questions at the moment? Yeah, go ahead.
So you don't need to like, when you make the sample space, you don't need to like label that this is referring specifically to tails on it.
Well, it depends on what they were doing. If they, for example, were doing something like part A, if you were tossing 2 fair coins and just recording what the outcome was with both, S would have been TT, TH, HT, and then HH for those outcomes. But it's only because they said record the number of times tails is facing up, we had to put that in. Does that answer your question though? Gotcha. Other questions at the moment? Okay, thanks for all the questions. These are really great questions. Really the things that I would want to mention if they weren't a question. So that's excellent. We have the sample space. This one is complicated by nature, especially since it's the first time we've done this kind of thing. And now that question is also complicated. It says, are the outcomes equally likely? What are the outcomes? They're talking about these 0, 1, 2. They're not talking about these ones at all. These are the outcomes that they actually recorded in their total experiment, saying how many times tails was facing up. And how do folks feel about this one? Does it feel equally likely, or looks like a lot of people shaking their heads no right away? Anyone on the contrary? Well, I agree with you all. These events are equally likely, but those are not the events of this chance experiment. Any one of these four could happen equally likely. But when we go here, that one's the odd one out, right? One actually occurs twice as much as all the others. So we really don't have equally likely events at all. I'll put here these events are not equally likely. Let's see if we can give some explanation to that. Like we did before here on part A, we said they were equally likely because we calculated the probability of those events and we observed they're equal. In other words, equally likely. Let's do that same kind of procedure here. Let's take the probability of all these events here and just see what we come up with. First thing I would do is say the probability of getting a 0. We have to count, well, what are the number of ways you could get a 0? There's only one way. We've got heads and heads, or excuse me, heads and heads. Don't know what I was about to say there. So one goes into that numerator. Then we divide by the total amount of possibilities here, which would have been 4. So getting a 0, that's going to happen 1/4 of the time. That only happens, and that value right there. Next, let's take the probability of a 1, only because it comes next. Probability of getting a 1 in this experiment is, well, now there's 2 ways that can happen. You either tossed a tails or the head, your first coin was tails, your second coin was heads, or you tossed head tails, vice versa. That means there are 2 potential ways of getting an outcome of 1 out of 4 different possibilities in this list, gives us a 2/4 or a 1/2. On the 1/2, we could call that a 0.50 if we prefer, or it's also just fine to leave it as a fraction. There's nothing wrong with 1/2 as a number there. And again, you could even make it a percentage as you want. Likewise, let's call the 1/4 a 0.25. Let's take them all to a decimal form. Finally, the last one, if we take the probability of 2, this is the same as the probability of a 1. There is only one way to get a 2 in this chance experiment. We tossed tails twice. So that one possibility is our numerator. The 4 different potential ways to get a number is our denominator. And now we're back to 0.25. And here we can see right away, they're not equally likely because, well, all those probabilities are different. Well, I mean, not all of them. The middle one is the odd one out here. Well, that's how this kind of problem goes. Any questions at all, folks, on running through this example? Yeah, go ahead.
So since all the probabilities have to add up to 1, like in this case, that is just happening through percentages.
Exactly, yeah. And same in this one, these probabilities here and here also had to add up to 1 as well. Other questions or comments? Okay, well, let's take a look at the next definition on this. The definition for a so-called event. This is kind of a tricky definition right here. So this example 2 is going to have some ramifications for what happens to formulas when we go to take probabilities. You can take the whole probability of a sample space, for example, or we could take a probability of nothing ever happening. But to discuss those weird probabilities, we have to discuss what an event is. An event is any collection of outcomes from the sample space of a chance experiment. And when they say any collection, they really truly mean any collection whatsoever. Or a more mathematical way to say it is any subset of the sample space itself is automatically an event. Well, that's a tough definition, and the best way to do it is we'll refer to something we've already created, a sample space ready to go. We'll use example 1, part B. So let me grab that sample space. So we've got a sample space, and our goal is list all of the possible events on this thing. It's a really kind of a strange process. So let's give this a try. The events are we go to the sample space, and I'm going to take any subset or any collection of those three objects, call it a new set, and that's automatically an event. So first are the really simple events. You could have just a 0. The next event could be just a 1. Events are also sets, so we're using curly braces to enclose them. And the next possible event that contains just one element would be 2. So we took all the events that contain exactly one element. Now we're going to move over to the events. It could be any collection. So let's take 2 elements at a time. Any volunteers for the next set or the next event? Yeah, go ahead. Exactly. We can take 0, 1. If you start with a 0, I think a good way to think about this is now take 0, 2. The next one would be a 1, 2. And one thing about sets is I'm only writing down 3 of these. The set 0, 1 is the same as the set 1, 0. Let's make that an additional comment on the notes. 0, 1 as a set is the same as the set 1, 0, since sets are unordered. So all a set does is collect objects. It only shows the unique objects, so no duplicates. And order is totally irrelevant in a mathematical set. That means with these 3, I don't have to put down another set of 3. 1, 0 is the same as 0, 1. 2, 0 is the same as 2, 0, and so on. Now let's put down a comma because there is even more sets. We're getting to the weird ones. There are 2 more sets that we can take out of here, which we'll call an event. Anyone see what a next possibility could be? Exactly. You could take the whole entire thing. The sample space itself is a legitimate event. So 0, 1, 2. That's just the sample space S. So I'll emphasize it there with the equality. And there is one more set. This is the weirdest of them all, but we truly need it because we need formulas to come out of this. For example, the probability of the whole sample space is automatically 1. And if we think about that, the sample space contained all of the outcomes of this experiment. So what's the probability of getting a 0, 1, or a 2 after tossing the 2 coins? It's 1 for 100% chance. You're going to get a 0, 1, or 2 when you run this experiment. But there is another set here that gives us probability 0, something that's impossible that we actually need. That's the final event in this list, the weird one for sure. Anyone happen to know what it would be? Okay, it is, again, it is really weird, and it's more of a consequence of math and subsets. If you would talk about any collection of outcomes, the weirdest one is this collection. It's the collection that has nothing in it whatsoever. It would look like this, a set that opens and then closes to emphasize there is nothing in it. This is called the empty set, and it's written this way, a circle and a slash, a null set. So if you ever write your number zeros like this, then that could be misconstrued as an empty set, but it's context sensitive, so no worries. And it's meant to be the empty set. It contains no outcomes. And so if we put the empty sets right here, the probability that nothing happens after you toss 2 coins is 0. When you toss those coins, you're going to be able to resolve heads or tails, give a number 0, 1, or 2. So there is no way to get the empty set at all. But it allows us to get a 0 for our probability. We'll use that in our formulas coming up. And a 1 comes from taking the probability of the entire sample space. All of these in the middle, or let me highlight them correctly. All of these will give us different probabilities, like the 0.25 or the 0.50 and so on. But finally, that is the collection of all the possible events. Any questions at all, folks, before we call it a night? Okay, when we come back next class, we'll come right back to these notes. And we'll start doing more and more probability problems using these ideas and formulas. Have a great night, everyone, and I'll see you all next week. Hey, how's it going? Yeah, for sure.
This one, the negative intercept of the least square revolution line. And I just wanted to check out the explanation that says, when the distance traveled is 0 meters, that was if the time is 0, then that means the time hasn't started, there was no distance traveled, correct?
Right, you can't have a negative distance. I agree with that.
Okay, so that,
Yeah, I think I'm getting a little confused with that negative. Let me pull up the quiz though, just to double check. I think I might not. That was, I think something didn't print on that document. The PDF shows it should have said y-intercept. Yeah, sorry about that.
Oh,
So we were
We're
saying
like,
like
oh.
a negative
Yeah.
intercept, so would that be correct if there's 0 time, that means nothing has moved?
Exactly,
So that would be the stone.
exactly. Yeah, your reasoning there is correct.
Okay,
Oh, okay.
and then,
Yeah, I mean, this was a race, right? So that would be a 0-meter race. That'd be really boring event on
and
TV,
then
right?
it would be the same as he like saying each meter we gain, we expect to increase the time by 0.15 seconds.
Now, let me take a look. So your slope is that. Yeah. Yeah, for each additional meter of the race leg, your record time goes down by that amount.
Okay, and
Or, let me see. The record time should have increased actually. Really?
yeah.
This, if we drew a line through this, it would have.
Oh,
had a
no, I
positive
said, yeah,
slope.
as we gain a meter, we expect it to increase. right?
Okay, yeah, that
Okay.
sounds great.
And then, that one, for example, you plug in the number for that.
Mhm.
Okay, and then this one, would it be a time problem?
Which problem are you looking at?
Like, would it be like, the time would be unpredictable that far, or it can be a record time because of how far it is?
Well, it's kind of a different issue. It goes back to, let me pull up 4.2.
Oh, Lord. Sorry.
Oh, no, you're good.
I was like sitting here, I'm like, oh, that negative intercept messed me up, so I had to
Yeah.
ask about it.
So the issue with that last question there is similar to what happened on this one.
Okay.
We're making a prediction at 250 for a mini right meter,
Yeah.
but 250 is nowhere in sight with this data. So even though you can get a number,
Oh,
it's
so
considered extrapolation.
because it's not, it wouldn't be in the value.
Yeah.
Of the range we're measuring, so it'd be an
Here,
outlier. really,
exactly.
really far.
This only goes to 5,000. We're going 10 times further.
So it wouldn't be on the list, and wouldn't, we couldn't calculate that properly. with
Right.
all the others.
We could calculate, but we would never trust the result.
Because we have results here, but calculating something like that would be way. far.
Yeah, I mean, you could do like 5,100 or maybe 90 meters or anything in the middle of these, but you can't go way, way outside that data.
Okay, well, that makes sense. Thank you so much.
Awesome, you bet. Any question over here?
Yeah, I just want to verify. I think I'm like, I kind of just want to write this down fresh because in my head, I think that I'm like mixing it up. So I just want to make sure that I am using the right like setting on the calculator to find least squares regression line. and,
Gotcha.